Let's classify matter. Matter can be split up into two groups, homogeneous and heterogeneous. In homogeneous, everything will be the same. In heterogeneous, you are going to see differences. Heterogeneous substances are heterogeneous mixtures. When you look at a heterogeneous mixture, you will see that it doesn't stay mixed, that it will separate out. A good example of this would be paint. So paint, it looks like it's mixed, but if you let it sit for a long time, you're going to get different layers. So the larger molecules are going to sink to the bottom, the lighter molecules are going to float to the top, and you can get it back to being mixed more evenly, but again, over time it will separate itself out. Homogeneous mixtures can be split up into pure substances, which are elements and compounds. So if I have just one element or if I just have one compound, that is considered homogeneous because everything is the same, even down to the molecular level. In this unit, we are going to be talking about homogeneous mixtures. And homogeneous mixtures, another name for them, it is a solution. And you should know both terms, that a solution is a homogeneous mixture and a homogeneous mixture is a solution. These solutions or homogeneous mixtures do not separate out over time. They are always going to stay mixed. So if you have, say, a bottle of Gatorade, putting that on the shelf is going to stay Gatorade. It's going to stay mixed. It's never going to separate out. Now, solutions do not have to be just liquids. They can be different phases of matter. They can be gases, they can be solids. A good example of a solution that is a gas would be the air that we're breathing. So we have a mixture of different elements and different compounds, and they are mixed evenly, and they stay mixed evenly. We don't walk through the room from one pocket of oxygen to another pocket of oxygen to breathe. Instead, that oxygen is just mixed in evenly in that nitrogen gas. About 80% of the air we breathe is nitrogen gas and about 20% is oxygen, and then there's some lower percentages for other things. A good example of a homogeneous mixture or a solution that's a solid would be lead solder. So that is composed of lead and tin, and it's melted together and it makes a solid homogeneous mixture or solution. A solute, that is the component in lesser concentration, or that is the thing that dissolves. The solvent, that is the component in greater concentration, and it is the dissolver. And how I memorize solute and solvent is I remember alphabetical order, and I draw it like this. So U, V, and I know that the solute goes into the solvent. The most common solvent, that would be water. Water being polar, it dissolves a lot of salts, a lot of ionic compounds. In the laboratory, we use a lot of ionic compounds, and water is known as the universal solvent. The definition of solubility, this is the maximum amount of material that will dissolve in a given amount of solvent. And that would be a saturated solution, meaning that there's only certain amount of area in the mixture that can hold the solute. Now remember your solubility rules. So all nitrates are soluble, all alkali metals like sodium ion, potassium ion, lithium ion, those will all dissolve, and all ammonium compounds. And so we are going to be using these solubility rules throughout this whole unit. Just some more terminology. Miscible means that the components will mix no matter the proportion. And a good example of this is alcohol and water. So in this case, there is no saturated solution. It doesn't matter how much alcohol you have or how much water that there is, they will always mix. And you should know that all gases are miscible with each other. So it doesn't matter how much gas you have or what gas it is, they will always mix. As far as the alcohol and the water go, I have a picture down here because they both have that hydrogen bonding and the dipole-dipole attraction. That is why they will always mix. Your solvent will never fill up with the solute. And it doesn't matter if the water is the solvent or the alcohol is the solvent. If I have more alcohol, that would be my solvent. If I have more water than the alcohol, then that would be my solvent. In this next picture, we have oil and water. These are immiscible, so these do not mix, and it has to do also with the polarity. You do get the little polar heads of this is the oil or the fat molecule, that you can see that will dissolve in the water, but the nonpolar tails, they will not dissolve. And so we get oil and water are immiscible. Solutions form due to the natural tendency to mix and spread. In other words, their kinetic energy, their collisions with each other and with the sides of the container. And this is just a spontaneous process. And this applies to the liquid and gas states of matter. They will automatically mix. So in this picture, we have some dye put into some water, and it will eventually be completely blue as the water molecules collide with each other and with the liquid dye until we get everything is homogeneous, everything is dissolved. In this process, the entropy or the disorder increases, and we are going to have a unit on entropy in the future. But I'm putting this here just so as you go back and restudy this before your AP test, then you will know what this term means and you can apply it to your knowledge of solutions. Solutions also form due to the types of intermolecular forces. It can prevent or cause solutions to form. Now down here at the bottom I do have gases, and these gases, again, gases always mix no matter what. So in this case, it applies to that natural tendency to mix. Intermolecular forces interactions, we can have solute-solute interactions, solvent-solvent interactions, and solvent-solute interactions. So in other words, in order for something to dissolve, the solute has to come apart, the solvent has to spread apart to allow the solute to dissolve in it, and then you have the solvent-solute interactions, where the solvent completely surrounds every solute particle. Let's look at sodium chloride dissolving in water. So when you have your solvent surround the solute, that is called solvation. If the solvent is specifically water, it is also called hydration. So hydration is just a specific solvation. In solvation, the solute will attach to each of the solute particles and pull them away from each other. And this is called dissociation. Here we have a solute particle and it is surrounded by those water molecules. So notice the water molecules are so very, very tiny and the solute particles are a lot larger. And there is a particular way that they combine. If you look at water's polarity, you'll see that the positive ends around the hydrogen of the water, they will surround the negative anions of, in this case, my ionic compound, sodium chloride. And then you get the negative ends of the water molecules surround the positive cation, or that sodium ion of my sodium chloride. I will link a YouTube video so that you can see a simulation of how the salt dissolves. So make sure you take a look at that. When you get that ion separated from the other ion with the water molecules surrounding it, you get what's called an ion dipole interaction. This is not an intermolecular force. This is just another force of attraction, and it happens in solutions. Here they have 5 water molecules surrounding this ion. Typically there's around 6, so you would get 4 around the equator, so to speak, and 1 on either side of the poles. Let's review what happens when you put an ionic compound into water and it dissociates. So look at this first example. We have table salt or sodium chloride. We're going to use our periodic table to look up the oxidation number. And so sodium has a +1 oxidation number, and it's a 1-to-1 ratio, so that means that the chlorine or the chloride ion must have a -1 oxidation number, and it's a halogen, so they would have a -1 oxidation number. It is balanced for charge and also atom. So we have 1 sodium on each side, and it's neutral on this side, so I'm just going to put a little 0. And this is a +1 and a -1. On this side, it is neutral on this other side. And we see that it splits up into 2 particles. Let's look at the next one. We have potassium nitrate, and all nitrates are soluble, and it's with potassium, and potassium's an alkali metal, and all alkali metals are soluble. So looking on the periodic table, we get a K+1, and then this is nitrate. You should be familiar with that. It stays together, so don't split it up into nitrogen and oxygen. It's NO3-. We look at the number of particles it makes. It also makes 2 particles. And let's look at the last one. We have sodium phosphate. So sodium, we just did this one up above. It's a +1. And phosphate, I can figure out the charge because it's with the sodium. it's a -3. It is neutral on this side, and on this side we have it not balanced as far as charge goes. I need to put a 3 in front. This would give me a +3, and this would give me a -3. And adding that up, I do get neutral on this side. So that's balanced for charge, and I would discover that if I balanced it for atom too. So 3 sodiums, and I have 3 sodiums, one phosphorus, and 4 oxygens. So this is balanced. Non-electrolytes or molecules, they can also dissolve in water, but they would have to be polar, and that's what we see here. So we have sugar, which is a solid, and when we put it in water, we get sugar that is aqueous. It just means it's dissolved in water. And we do see that the water surrounds the sugar. You can see those water molecules. It hydrogen bonds with the sugar, that's why it dissolves. And notice that the sugar stays together. So I only have one particle. So we don't get a great dissociation. It just dissolves. It stays together. On this slide, we're going to do just more practice with dissolving different compounds. And we're going to look at what's called the Van Hoff factor. This is the number of particles it splits up into. Salts will have more than one because the cation and the anion split up. Strong acids will also have more than one, and also strong soluble bases. And I realize that we have not talked about strong acids and strong bases, and so I will tell you if they are. But if they are strong, that means that they will dissociate. Your weak acids and weak bases, they tend to not dissociate. They tend to stay together, just like that sugar molecule did in the last slide. I will tell you that. So later on, after we do acids and bases, I would expect you to know this, but at this point I'll always tell you if it's strong or weak. Let's look at this first one. So all sodium compounds are soluble, and this is a strong base. So sodium is a +1, and then what makes it a base is this hydroxide group, this OH group, and keep it together. So it's an OH minus, is a polyatomic ion. The Van Hoff factor is given the symbol of a little cursive I, and because there's 2 particles, then the Van Hoff factor is 2. Let's look at this next one. Calcium nitrate. All nitrates are soluble. So this one, calcium is a +2, and I have nitrate -1, and to balance it, I would put a 2 there. Just double check and make sure that it's balanced for element and charge, and it looks like it is. So neutral on each side, and so I have 3 particles when I put this into water. This next one, this is an ionic compound, and we have our calcium there and our phosphate. That I need 3 calciums for every 2 phosphates. I end up having a common multiple of 6. So this is actually a -2. A -3, excuse me. I'm going to put a 2 in front there and a 3 in front there, and it should be neutral. So let's see, this is a +6, this is a -6, and that's neutral because this side is 0. My Van Hoff factor in this case is a 5. And let's look on the next one. This is hydrochloric acid. It is a strong acid. It completely splits up. So we have hydrogen with a +1 and chlorine with a -1, and we get 2 particles. This next one, this is a weak base, and you should know that weak acids and base, they don't dissociate. So it's going to be a little bit like the sugar where it just stays together. So again, just 1 particle, pretty close to 1. Just because you're combining a solid and a liquid doesn't mean that you're dissolving. In this case, we have nickel reacting with a strong acid, and I do get a nickel chloride solid. And so this is a case where a chemical reaction has taken place. So just because you have a liquid and a solid combining doesn't mean you're dissolving it. You could still have a reaction. When you make solutions, the polarities must be the same. What this means is that if I have something like water, which we know is polar, it will dissolve anything that's polar. So I can dissolve salts, ionic salts. I can also dissolve polar covalent molecules. Remember, ionic compounds or salts, they have extreme polarity. So you have a positive ion and a negative ion. So most salts, they will dissolve in water because they'll be able to pull apart. In this case, we have ionic salts, which is extremely polar, and then polar molecules, they will dissolve in water. And so the polarities match. And I have a picture here of 2 polar bears to help you be reminded of this. So polar dissolves in polar. Looking at the little small brown bears, these are not polar, and so non-polar dissolves non-polar. So if I had something that was non-polar, like let's say hexane, where I just have carbon and hydrogen, if I were to add something that was non-polar like iodine, we would see that it would dissolve. So if the polarities don't match, then it's not going to dissolve. So if I put iodine in water, you would get no solution. Or if I would put a salt into hexane, you would get no solution because the polarities don't match. Especially this nonpolar solvent right here, it's only has dispersion forces holding it together, and there's no way that it can pull apart the ionic solid. The dispersion forces just aren't strong enough. So looking at this first picture, I have copper 2 sulfate dissolved in water, and we do get an ion dipole formed. So the water will totally surround each of those ions. So here's my Cu2 plus ion surrounded by waters. Notice it's the oxygen ends that are negative that are closest to it. And then we see the sulfate group, which is a -2 charge, and we see the hydrogens more attracted to it. So this is my -2 polyatomic ion right there. And you can see the water, the hydrogens are closest to it. If we put our salt into hexane, the dispersion forces are too weak to pull apart the ionic bond, and vice versa. So if you had water and you had the iodine, there's really nothing for the water molecules to grab on with the iodine because the iodine is nonpolar. Let's look at this bottom, number 3. This is a case of a solute being non-soluble. You might think that it would dissolve in water, but when you look at it, the calcium has a +2 charge and the carbonate is pretty large, and it's a -2, and the lattice energy is just too large for the water to be able to pull it apart. So this will end up staying together as a solid, so it is an insoluble compound in water. Not because of the polarity, but because that ionic bond is so much stronger than any ion dipole that the water can form. So if you look at these compounds up here, these are all polar, so they are good candidates to dissolve into water. And these right here, these are all nonpolar, so these are good candidates to dissolve in a nonpolar solvent. They do measure the polarity for there. It's measured in debye's, and so the higher the number, then the more polar it is. And we see that there are 0 debye's for these 3 down here at the bottom. If I take a nonpolar substance and combine it to a polar substance, a lot of times you do get a separation right here where you will get the nonpolar clinging together and the polar clinging together. The process of dissolving can be exothermic or endothermic, and there's some steps that have to occur. So the first step is the solvent has to pull apart, so to allow the solute to fit in the solvent, and that tends to require energy. It's endothermic. The second step that has to happen is the solute has to pull apart. So the cations and the anions have to pull apart, and that takes energy. That is also endothermic. So I can take those 2 steps I just talked about and I can put them together. And then when they actually mix, that tends to be an exothermic process, or energy is released. You can compare this step 1 and 2 to the mixing, I'll call it 3. And you do what you start with minus what you end with, and you end up getting an overall net exothermic reaction. So there's more energy given off when it mixes than pulling the solvent apart and pulling the solute apart. So this would be an exothermic solution process. Let's look at the second one. This second one is an endothermic process. Notice that it kind of has the same steps here. So first of all, you pull your solvent apart, then you pull your solute apart. You can add those up. And then again, it's exothermic when you mix it. If you take the initial minus the final, in this case, it ends up being overall putting more energy into it than what you get out. So your enthalpy of mixing in this case is positive, where this one is negative. So why does this one dissolve? And it's because the disorder is increasing. And so that is what's going to drive the reaction. And I know we haven't talked about entropy, but we will later on. I just want to put that term in here in case you're reviewing for the AP test. So again, splitting up the solvent and the solute, that requires energy. The mixing releases energy. And if you release more than it required, then it is exothermic. If it takes more energy to split the solute and solvent apart than it does to mix them, then it would be endothermic. So overall, if it's endothermic, the solution will feel cold when you mix it together. And if it's exothermic, the solution will feel warm. So most of the time we do get this. We get more energy released than is required to split it apart. And these charts right here, these just say the same things as those last charts do. So again, split up the solute, split up the solvent, and then when you mix it, you're going to take that difference in energy.